As it states over here, a capacitor is an electrical component that stores electrical energy in an electrical field. All the material used on this video is based on NIST modules number 2. To get a PDF, please check the link in the description of this video. To better understand capacitors, we need to understand electrical charges. So whenever we have a negative and a positive charge, they are unlike charges, they actually attract to each other. So here we got this one trying to pull into the negative. Alike charges, they push each other away, and that's what these two are doing. They're pushing themselves farther away. Capacitors consist of 3 parts. Here we got a plate that usually it is just a piece of a very thin metal plate, one on top and one on the bottom. In between, sandwich, there will be an insulating plate. So it will be plate A, plate B, and the insulator, which is called a dielectric. As you can clearly see over here, we got a symbol of a battery. This is a 2-cell battery, and we got the negative with this switch closed attached to the bottom plate, and the electrons that are in this plate, they actually flow, electrons from the battery flow into the plate, and it fills this bottom plate with electrons. The top of the battery, since it's positive, the electrons that are in the top plate, they flow into the battery, so therefore there is a depletion of electrons in here. So since there is per se holes, so now that is at the positive potential, and in here at the bottom we will have an excess of potential. Because of that, the electrons from this plate will always try to jump across this barrier into the positive plate. But the barrier is also made up of its own atoms, but they happen to be in such a way that are balanced that they just do not release the electrons. So therefore they perfectly insulate. So it gets polarized the way how you see it, and pretty much this acts like a wall. So these electrons are pushing, trying to cross the wall to fill in the depleted holes. If we were to open the switch or eliminate the battery altogether, then there will be a charge between these two. So in essence, you could think of a capacitor as a battery, but it's not. It's a battery that it doesn't hold that much power. Now, if we were to touch with the wire the top plate with the bottom plate, immediately there will be a short circuit, which it will damage the transistor. But the idea is that it stores energy. Capacitors comes in different shapes, but these are two of the most popular ones. We got the little ceramic capacitors, and inside the ceramic capacitors we just got, well, the protective covering, which is what you see here. And then here at this part you see one plate, in the center you see the dielectric insulated, and then they did not draw it, but on top of it, it should be another plate, which it would be another the one plate on top and one plate on the bottom. So you will have the same concept as we saw in a moment ago, and a dielectric in between. You will charge one side positive, and those and then the other plate, the one that will be negative, the electrons from that negative will be trying to go into the positive one. Here we got what is called an electrolytic capacitors. Electrolytic capacitors are polarized. Notice that in here it has this little symbol, and this means that this got to be connected to the negative side. You see this little this little curve over here. This is an electrical symbol for a capacitor. Whenever you see this in a circuit, that means that when you had to hook up this little leg, you had to hook it up to the side where the curve is. This is the positive side, this is the negative side. This capacitor in here does not have polarity, and those are the ceramic types. The electrolytic capacitors, which is the ones that are polarized, they can hold very large amounts of power compared to the little ceramic ones. Here we got the inside of an electrolytic capacitor, and all it is a little plate. And when I say a plate, it's not, don't think about a really solid metal plate. This is, if you think about it, it looks like foil paper. Like if there was foil paper on the bottom, and then it looks like plastic tape when you open them in real life, and then on top of it you have more foil paper. That's how you make a capacitor. As a matter of fact, if you want to make your own capacitor, you can just simply take foil paper on one side, electrical tape in between, and then more foil tape on the other side. But the catch is that the top paper cannot be touching the paper on the bottom, so the foil paper is going to have to be smaller than the actual electrical tape. It's not going to be the best capacitor, but it will be a capacitor, especially if you make it very big or very large. Remember that the barrier that is in the center is always called the dielectric. That's the proper terminology. Going back to how capacitors are drawn on the schematics, here we got a symbol for a capacitor. This is a non-electrolytic capacitor. This is just a regular ceramic capacitor. Just here is one, and here is another one on this circuit. By the way, as a review from a previous video, you can see that these are inductors. So now you know how a capacitor and inductors look on a circuit. There is a variant to an electrolytic capacitor, and it's this one. Some manufacturers, like I said earlier, it will draw it with a little indentation, a little curve, and some other manufacturers, they will just draw it this way, where one side is darker than the other one. That is an electrolytic capacitor. The polarity on this one matters. If we put it backwards, it will get destroyed once we energize the circuit. Here I got page 3.6 of the NIS module number 2, and this page over here, it just covers some of the constant values that different dielectrics offer within capacitors. Dielectrics are very important. The better quality dielectric that you have, the more charge you can store in a capacitor. The bigger the plates are, also you could store more power within a capacitor. But this is more to do with capacitor design. This is more for interesting reading rather than becoming a great technician. Just as we saw with inductors, capacitors also have time constants. Here we got a capacitor that, as it's charging, immediately as soon as power gets attached to it, and the capacitor will charge in 5 times. Within the first time, it's going to charge to 63.2%. Then by the second time of the capacitor charge, it's going to rise another 63% of whatever is left from this point to this point, which in this case is going to equal to about 86.5. From 86.5 to 100%, there is another, I guess, 13.5 percentage more to go. Well, the other 63.2, it will take us to 95, and so on and so forth until we get here, which is very close to 100. So capacitors, where they charge the more is at the beginning of the time constant. The time constant for any capacitor, it is defined by, see, the wires that are going into the plates, they have certain resistance. That resistance of those wires times by the capacitance, which, by the way, capacitors are measured in capacitance. So the value of the capacitance times the resistance, it is what's going to give you the total charging time constant for charging a capacitor. Now, When I mean the time constant is one of those 5. So the value that's going to give us here is going to be the time that it takes to go from this point to this point, which is going to be the same time it's going to take me to go from this point to this point, and so on and so forth. So in reality, the whole total time is going to be time times 5. And that is what's going to be the whole time for both charging or discharging of the capacitor. This is the part that I had never talked about, but capacitors, they charge in a very curvy way per se, and they discharge also in a very curvy way, to where they discharge most of the charge in the first time constant, and they give away about 63.2% of their power, and then the next time they discharge the other 66% of whatever is left over. When we were talking about inductors, we said that voltage leads current. In capacitors is the opposite. Current leads voltage, and the acronym is ICE. As soon as I attach a battery to it, electrons start flowing. And if you notice, it goes through the resistance, and they go and they start charging the capacitor. So the capacitor is being charged. Also, electrons are leaving the capacitor, so we're gonna have very positive potential here and negative potential here. As time passes, that current flow at the beginning starts very large, but as time goes, it's gonna become less and less and less, because the plates are gonna be saturated with negative electrons in one side and too many holes in the other side, to the point that it's not gonna be any more electrons left in this plate. At that point on, current is gonna go low. So at the beginning, if you will, the current in a scale, it starts really high, but eventually gets to no flow, which is when the plates are totally filled. As current is flowing, the capacitor in the essence kind of looks like a short, because it seems like electrons are going through it. So the voltage starts with 0. But as the capacitor starts charging, it starts accepting less and less electrons, which means current flow is going low, like I indicated a moment ago. As that happens, the voltage across the capacitor starts increasing until it finally will be the full potential of the battery. So if I got a 9-volt battery, I will end up with a full potential of 9 volts, and I'm gonna do this line. So this is my voltage, and this is my current line. And this is what explains why people say that current starts really flowing big at the beginning, and therefore current is leading voltage, because the voltage starts at 0 volts and eventually goes, once the capacitor is charged, the capacitor will act as an open. And when you got an open on a circuit, you will get a full potential reading across all the leads. It will act like, it will be the same thing as reading an open switch. Therefore, I can say that in a series system, if I apply a DC voltage, immediately the capacitor, yes, is going to allow electrons to flow. This will get power for a very short period of time. But then, once the capacitor is full, the resistor is not going to have any electron flow, so therefore it's not going to be producing energy or consuming power, should I say. So it will be like disconnecting from the switch. So we can say that capacitors block DC, but they pass AC. So I got an AC signal over here. Remember, an AC, what it means is the electrons are traveling first one way and then the other way, and they go back and forth. Yes, it's true that as electrons are coming to this way, they will full, the capacitor will get full, and then it will block the last end of that particular wave, and then what's going to happen is that now the electrons are going to start flowing, because that's the nature of AC. The opposite way, causing to this charge, and the capacitor, since it's going to have some extra force, it's going to send those electrons back over there and the next way. So now what it's going to do is from the point of view of the resistor in this case, is that, see, if I make this a little bit rounded, what the capacitor is going to do is just going to make this roundness more like square at the beginning, meaning that it kind of works like a filter. But anyway, that's just something extra that I wanted to add. At the end of the day, what I want you to get is that, first of all, capacitors, they store power and they block DC and they pass AC. Later on, we're gonna cover rectifiers. For right now, I just want you to understand that a rectifier, all it does is converts AC into DC. So this little wave over here is this one over here. Now this one over here that is down at the bottom is this one over here, so it's number 2. The third one is that one. This is the fourth one, which is this one here at the bottom. So really what the rectifier does is just takes the bottom ones and just flip them up. But the problem is that this DC is kind of like wavy, so it is not smooth. To fix that, one quick way to fix it is to put a good capacitor right there at that side. And what happens is that in this part the capacitor is going to charge, but when it gets to here, as power starts decreasing, the capacitor starts giving out the power that it got, and it starts filling in the blank, so to smooth out the signal. At the end, really, the capacitor is just gonna, well, like I said, smooth out the signal, smooth out DC signal. That is one of the biggest functions that you're gonna see capacitors use as an EM. Now let's talk about a capacitor max working voltage. So here we got a battery, and we want to just use a capacitor to smooth out the signal. And what it is that since we put in 12 volts to the capacitor, we should go 50% max of the max value. So 50% of that, 50% of 12 would be 6. So I should use an 18 volt capacitor for this circuit to be safe. But if I change and now I put a AC source of 12 volts, 18 volt capacitor will not work because peak to peak. I talk about peak to peak of AC on our AC to DC video, or AC and DC video, which is video number 2. When dealing with AC, we have to worry about that peak to peak. So here I got 12 volts multiplied by 1.41, which is how we can get back to peak from RMS. 12 volts is RMS. That's what they always, if you buy a 12 volt power supply, it says 12 volts, it's given in RMS. If you measure it with a multimeter, you will get RMS. But if you multiply that by 1.41, as I explained on AC and DC video, I get somewhere roughly between 17 and 18 volts. I don't have a calculator, so that's why I'm giving you those values. So to use a capacitor for that one, now we have to do 50% of whatever this value is. So let me choose 18. Half of 18 is 9. So 18, which is the maximum actual voltage that I have, plus 50% of that, which is 9 volts, it will equal to about 27 volts. I will have to choose a capacitor for the previous circuit of 27 volts. When adding capacitance, if parallels are connected in parallel, as I got them in here, all you have to do is add the capacitance of one to the other one. And it makes sense because some electrons are going to here and holes over here, but this other one is also getting the same one. So therefore, from the point of view of whatever, first the battery to charge it, and then once I hook it up to a load, both capacitors as tanks are going to be providing electron flow to whatever the load is. So in parallel, we just simply add the the capacitance just straight on that formula. And here it means that if we had 3 capacitors, we just simply Cn will be up to the number of capacitors that it would be in that circuit. Now we got capacitors in series. So C1 is in series with C2. If you will, here there's a dielectric and it has certain distance. Now we have double the distance of the dielectric. The farther the away or the thicker the dielectric is in a capacitor, the less the capacitance of the capacitor is going to be. So with that, we just simply added twice the amount of dielectric by putting them in series. So therefore, in series, capacitance really is going to be always going to be less than the smallest value. And if you use this formula over here, we just simply plug in whatever value we got here into that one, whatever value we're given to this one there, and we just simply 1 divided by that, and then we add that to 1 divided by that, and then if we have more, we just continue doing the same symbology. At the end, to properly mathematically clear this formula, we're gonna have to, well, pretty much do this, where the total capacitance is gonna be to that 1 divided by whatever values we get from this addition. So there's gonna be a very small number, even smaller than the smallest number. So if this capacitor was, if this one's gonna be 0.1, but this one over here was 0.0.0, the final capacitance that we'll get over here is gonna be a value that is even lower than the lowest point that we have. Finally, we got to end up talking about capacitance reactance. And that is the resistance that a capacitor offers to AC. For inductors, it was inductive reactance, as this was the formula. These parts, they look pretty much the same. It's just that in here, for inductors, we're using the L for Henrys, which was inductors. For capacitors, we use the C. The unit measurement of that capacitance is actually in farads. And so the formula is a little bit different because this one is 1 divided by 2 pi frequency times the farads. And that will give us the reactance, which is the same thing as the resistance. And it will be given an ohms for the capacitor. Now in this one, pay attention. If I make this number larger, the answer is going to be much smaller. So, if the frequency goes up, so if we drew it in here again and we talk about the same thing, if the frequency goes up on a capacitor, then its resistance goes down. Conversely, if the frequency goes down, the frequency that goes to the capacitor, if it goes down, then the capacitance reactance will go up. In an inductor, it was the opposite. Just remember this because this is the type of questions you get asked on your advancement test. Capacitors have 2 types of losses: dielectric hysteresis and dielectric leakage. There is no such a thing as a perfect dielectric, but if the dielectric leaks too much current, then at that point on it will leak to capacitor failure. Hysteresis losses, according to the statement, it says that it works similar to the hysteresis found on magnetic transformers or magnetic materials. Unfortunately, most of our multimeters, although they have resistance, they do not have the symbol of capacitance or capacitors. So therefore, we cannot really use our multimeters to test capacitors.